All right, students. Today we're going to be talking about the area of a polygon. So sides 5 through as many as you really want. Because as you know, we have area equations for a square, a triangle, a rectangle, but we don't really have them for 5-sided shapes. So I'm going to give you a formula that will give you the area of a rectangle, or for a polygon that is a regular polygon. Now remember, regular means that all sides are congruent. So every side has the same measurement. It doesn't matter how many sides you have, this formula will work for all of them. So what I've done here is I have inscribed a 1, 2, 3, 4, 5, 6, a 6-sided shape, which is a hexagon, into a circle. Now remember, in order to find this angle, you guys did this on your supplemental for Unit 9, I'm going to take 360 degrees, because that's one full revolution, and divide it by my number of sides so I can see how many triangles I'm going to have in here. If I do that, I've got 360 divided by 6 gives me 60 degrees. So each one of these central angles is 60 degrees. Now, if I want to find this internal angle of the hexagon, what I'm going to do is I'm going to take 180 times n, which is my number of sides, minus 2. So 6 minus 2 would be 4. So 180 times 4. And then divide it by my total number of sides, which is 6 in here. And if I do this equation, I'm going to end up with 120 degrees right here as my internal angle of my hexagon here. So then, in order to get the apothem is a perpendicular bisector. So any of your sides have a perpendicular bisector. That means it cuts this segment in half, so they are both congruent to each other here. And I end up with a angle bisector up here, because this is a perpendicular bisector. It's going to bisect this angle up here as well. So this was 60, so if I bisect it, it's now 30 degrees. And I end up with 2 right triangles. So in this case, I end up with a special right triangle of 30, 60, 90 through this perpendicular bisector. And this perpendicular bisector is called the apothem. Right? When dealing with a regular polygon, this perpendicular bisector is called an apothem. Now, if I take, and I already cut up all these shapes, I'm going to recreate this polygon using these shapes I already cut up. Oops. Almost there. So I have recreated this hexagon, but I've cut out all the right triangles. Now remember, all of these right triangles, there's 12 of them, because remember there were 6 triangles and I cut them in half, so now I've got 12. I've got 12 congruent right triangles. Now if you remember, the equation for the area of a regular polygon is the area is equal to 1/2 the apothem times the perimeter. There's your equation for the area of a regular polygon. And this should make sense. So if I take this equilateral triangle out here, and I pull one of these guys out, if you notice, the apothem of this triangle, this guy right here, so if I rotate that around, is actually the height of my triangle. So my apothem is the height of my triangle, and if I'm trying to find the area of a triangle, you guys know that is 1/2 the base times the height here, right? So that 1/2 makes sense, because I'm going to be using half of these guys. So if I take these off, and I start rearranging these guys into a rectangle, just like what we did before, when we were trying to derive the area of our shape earlier this week. Keep going. Okay. So I have taken all those triangles and I've created a rectangle now. And you'll notice that this guy right here, if I take that as my base, because it's the longer one, if I take this as my base is half of the perimeter, because it takes two triangles to create one of these little rectangles. So my base of my rectangle is 1/2 of whatever my perimeter is. And then if I look at this as my height of my rectangle here, then the height is just the apothem. So I end up with, if I take my base, which is half the perimeter, times my apothem, that gives you the area of a regular polygon. And this will work for every single regular polygon.